Let's take a look at the example. So EPA guideline for the minimum safe level of the radon in a home is a 4.4. Yeah, I don't know what is a picocurie per liter of the air, but anyway, the measure is 4.4 is the maximum safe level. When a home is tested, the number of measurements are taken and averaged. So a homeowner would be concerned if the average radon level is too high. In this case, a homeowner would choose a right tail test. Because why we collect the information? If we see the mean is so why we call it mean is because we are measuring the radon, not only the 1 point, several points in the house, right? And then we calculate the average. If the average is greater than 4.0, then you might concern. So now, let's say you got a 4.05. Now, this is a more than 4.0. But since you are randomly sample, so somehow, is it the 0.05 is this is the difference between 4.0, right? This is large enough. My mean is slightly bigger than 4.0, but is it because this error can happen only because it's a random sample? Random sample means you can have a little bit higher, you can have a little bit lower than the true means, right? So this is our sample means, but still my population mean can be 3.9, right? But even though my population means 3.9, still there's possibility I can get a sample mean 4.05. So can we tell 4.05 is really significantly greater than 4.0 so that we can say our house mean radon level is greater than 4.0. So our evidence, what we are trying to collect the evidence is our mean, the real population mean of the radon, average radon level is greater than 4.0 or not. Why we call this is one side? Because if it's smaller than 4.0, doesn't matter, it's like it's 1.5, this is far away from the 4.0, but that doesn't matter, right? This is 3.0 or 3.9, all the same. So I don't care this side. I don't care about the 4.0. I don't care about the smaller side. I just won't care about if this is significantly large. This is the problem. So I don't care about the smaller side, but I'm concerning about this bigger side. This is a one tail test. And then the null hypothesis will be the mu is smaller or the same as 4.0. Here the 4.0 is the mu naught, right? And then the alternative hypothesis is that mu is greater than 4.0. So we are trying to reject the null hypothesis, then either we success or you fail. So that's how you decide the null hypothesis and the alternate hypothesis. So now, is it large enough? So it depends on the standard deviation. If this is not large enough, how about 4.1? How about 4.04? So we will make a conclusion, the statistical conclusion, that we can say our average, the mean, population mean is actually greater than 4.0 or not. Of course, here again, this is a statistical conclusion. So decision rule is can we have a strong enough evidence? So strong enough means it's an extreme outcome. The underlying logic is like that. If the radon level is exactly 4.0, so our house true population average is 4.0, but let's say we got a 4.1. So is it possible my true population means 4.0, our X bar can be 4.1. But what is the probability we can have this number? Is it extremely rare case or not? If this is the pretty high probability we can have a 4.1, then we cannot tell our mean is greater than 4.0. But if it's a really rare probability, and we got this one, which means probably this is the evidence that the real population mean is greater than 4.0. So what we are testing here, the probability or the z-value, is we assume null hypothesis true, and then find the how rare cases of our sample mean. If this is rare, then you might say this is not happening by chance, because the real population mean is greater than 4.4. That's why we have a X bar is 4.1. Which then we can reject null hypothesis. So always we start with assuming null hypothesis is true, then we will find out how rare this case is. So we will find out the rejection reason, which means is when we trying to take this is smaller than or not, and how rare cases, how rare we can have. Then you can find the critical value. If the rare cases, the critical value, the statistical value is smaller than the critical value, which means it's a more rare case, then we can reject the null hypothesis. Two-tailed test is also smaller or bigger both sides. However, this is the dividing half. That's why the probability or the significance level will be different in the two-tailed test. And right tail is about is it really bigger than or not. So we will only look at the right hand side. But again, if we have the case is a kind of rare case, and we can say maybe the null hypothesis is not true, and we can reject the null hypothesis. So always we find out the statistical value or test statistics, we call that test statistics, or probability is under the assumption that H0 is the true, then we will figure it out whether our sample mean is the rare cases or not. Okay, so we will calculate the test statistics. Usually this is the z-value or the t-value. And then we compare the critical value. If our z-value test statistics is the rare case, then the critical value, then we will reject null hypothesis, because there's very low probability we can get that sample mean if we assume the null hypothesis is true. So which means this is not happening by chance, because the null hypothesis is not true. That's why it's happening. That's our conclusion. So how can we find the critical value? It depends on the alpha. So it depends on how you choose the alpha or confidence level. Then we can choose critical value. If our test statistics is more rare case. So left tail case is smaller than the critical value, and right tail test is greater than the critical value. So that's why I'm saying the greater than or smaller than. It's a more rare case, and we reject because it's pretty rare to happening, which means it's not just happening by chance, because our population, our no alternative hypothesis is true. That's why it's happening. So critical value is a boundary value. So this will be the boundary value. So the critical point, if our test statistics is smaller than or greater than this value, then we're going to reject the null hypothesis. So let's talk about the mean, testing a mean, and with a known variance, which means it's a sigma is known. So when sigma is known, what we use a z-value. So it's a simple, the known sigma, we will use a z-score. So test statistics is calculated by this one, but actually this, again, this is not the new formula. This is what? This is the z-value. Is the x minus mu over the sigma. But here our x is x bar. So sigma should be the x bar sigma. So x bar sigma, we know this is a sigma over square root of n. So you just replace this number, then you will get this one. That's the z value calculate. This is our test statistics. So this is my z value. So I will get a x bar, and I know the x bar standard deviation. So you can calculate my x bar z value. That's my statistics. And then you will compare depends on this right or left side, but if it's a right tail test, if your z value is far away from the mean and is greater than the critical point, the more rare case, then you're gonna say, if we assume the null hypothesis is true, but this is really difficult to get my x bar here, right? So which means probably this x bar I got is not by chance, because my mu is greater than mu 0. That's why I got x bar is here, which is pretty rare case if we assume null hypothesis is true. Then we can reject. But if the test statistics is within here, then maybe you got just a little bit greater number by chance, so you cannot say this is strong enough evidence. So critical test statistics will be compared with the critical value. Again, it can be smaller or greater, but if it's a more rare case, then we're gonna reject the null hypothesis. So you can see this number and this number and this number, but actually you can find this number from the z table. So level of significance is the 10%, which means, right? So what is the probability I can get a smaller than, this is the 10%. What will be this point? Which means I just consider the 10% is critical point. What is the chance I can get a number which is smaller than certain point? Will be the 10%. So this is the left hand side is 0.1. So if you look at the z table, probability 0.1 in between here. So minus 1.2 and 8, between 8 and 9. So minus 1.28 minus 1.29, right? So if you go back, so that's why it's minus 1.2 minus 1.282. That is the, in terms of z value. If the z value is minus 1.282, what is the probability I can get a z value which is smaller than minus 1.282 will be the 10%. So if you got something smaller than this z value, then the chance of getting those number is less than 10%, which means this is a rare case. So if you got a x bar which has a z value smaller than minus 1.282, probably that happened not by chance, then you can reject the null hypothesis. If the z value is greater than this one, which means even though null hypothesis is true, still you have a pretty good chance to get that x bar, so we cannot reject the null hypothesis. So critical point will be minus 1.645, which is 0.5, and then and so on. But the two-tail, actually this is just a plus and minus relationship, right? But two-tail case, because your probability will be divided into the two different parts, that's why you can have a different number here.